Morning, folks. Sorry I'm late. I'm not going to come up with a good excuse because I don't have one. So let's go ahead and get started here. Let me share the screen first. I do apologize. I am sorry about that. That's all I can say. Okay, let's see where we're at here. We had been talking about buffers. I hope you all got my email the other day. I talked about I had made a mistake on the buffer practice quiz. So I appended a new version of what I had talked about in at the end of the last lecture, and I believe that the math now is correct on that. I had gotten the step wrong. Let's see, this step here, the moles of initial minus the moles of NaOH and the moles of A minus initial plus the moles of NaOH. That math was wrong, and I ended up getting the wrong moles for the reaction because I did it in my head and didn't do the maths properly. Anyway, that's been fixed, so you can go back and take a look at that if you want to. All right, so we're going to continue now with finding the equilibrium concentrations of ions in solution. The plan here is to finish this part of the lecture maybe today, maybe partly on Tuesday. But the main thing is that the test 2 will be due on Thursday, I believe. I'll just check on that. But according to the syllabus, I believe that Thursday before spring break is when this test is going to be due. And that's, let's see, let me just check on this, make sure that I'm right here. Yeah, so test 2 review is set for next Tuesday, and then the test is going to be due on March 4th. So you can do the test any time up to that point, as it was with the first test. I strongly recommend not leaving it to the last day because there's just too much to look at. You know, if you're really serious about your grade, you're going to have to really look at this a bit more than just one day. It's just going to take more than that in order to get through it. Okay, so we're looking, let me get to, okay, so we're looking at the concentration of ionic species in slightly soluble salts. Now, the slightly soluble salt that we're talking about here is going to be magnesium hydroxide in this example. And this is the kind of question that you'll be faced with. Find the equilibrium concentrations of ionic species resulting from dissolving MgOH2. Now, the thing with MgOH2 is that when you put it into a container, some of it will dissolve. And by dissolve, I mean some of it will turn from a solid into ions. And the kinds of ions it turns into is going to be determined by, let me close that down. Is going to be determined by the picture of what we draw. So MgOH2, if I drew a picture of it, would be MgOH2, OH minus, OH minus, which makes the Mg2 plus. And then you can see how we would get those ions in the reaction here. That's not something you would be given. You'd never be given the actual reaction. You are, of course, given the salt, but you need to figure out how it breaks apart into its ions. So the kind of compound we're dealing with is going to be a solid that sits on the bottom of the container, but some of it will dissolve. And by dissolve, I mean turn into ions here. So when we're looking at the K expression, you can see it would be Mg2 plus OH minus squared over the concentration of MgOH2 solid. This is just products over reactants. The actual concentration of a solid, though, is not particularly meaningful because it's not dissolved in solution. So it's a kind of a constant value that gets tied up with the K. So what that leaves us is with the Ksp, which stands for solubility product, which is going to be Mg2 plus and OH minus squared. Easily derivable from looking at the solid and figuring out how it breaks apart. The square, of course, is important because that matches the 2 on the OH minus. Does anybody have any questions so far? What that means is that we can then go ahead and write out a table for the magnesium hydroxide. The initial concentration of ions in the solution is going to be nothing of each. If somebody could please mute, I'm getting an echo here. So what we're looking at is, again, the MgOH2 sitting down on the bottom of the beaker or flask or whatever, and it's not dissolved. What will happen, though, is at equilibrium, a certain number of Mg2 pluses will appear in solution, and double that number of OH minuses will also appear. So we're always going to get Z amount of Mg2 plus and then 2Z amount of the OH minus. So the number that goes in front of the Z will always be, of course, the coefficient. This is very similar to what we've already dealt with when looking at other similar K calculations. So what we can do then, if we know what the Ksp value is, and that is a constant value that we can get from tables, and that is given. Then what happens is we've got this situation here, 5.00 times 10 to the negative 11. Now these are always going to be small numbers for slightly soluble salts, because that's reflective of the fact there's not very much in the way of ions in solution at all here. So what I can do is substitute in the Z for the Mg2 plus and the 2Z for the OH minus. Now I haven't done the math here, but I will do it here for you at this point. So what that means is that Z times 4Z squared. So if you take 2Z and square it, you're also squaring the 2 as well. So it becomes 4Z squared, which if we transmit that to, or translate it to what we've got here, to be 4Z cubed. Any questions so far? Okay, so if we isolate Z, then it's going to be the cube root of 5.00 times 10 to the negative 11 divided by 4. And in your calculator, and I'd like you all to try this, please. In your calculator, what that means is you do 5.00 times 10 to the negative 11 divided by 4, and then you can do it to the power of 1/3. So this cube root here is equal to the power of 1/3. Does anybody have any questions? Is anybody uncertain about how they can do that in their calculator? The Z value that we get is going to be 2.32 times 10 to the negative 4. please take a look and make sure that you can get that value in your calculator. I'm going to wait a second and see if anybody has any issues. Okay, anybody have any questions? Okay. So the Z value, which would be the concentration of Mg2 plus, is going to be 2.32 times 10 to the negative 4. The concentration of OH minus is going to be 2Z, which is double that, 4.64 times 10 to the negative 4. Does anybody have any questions? Okay. So let's look at some more examples of these. We'll take a look at, well, we'll take a look at the kinds of problems you're going to see on the test. We'll also look at the practice quiz as well. I might do the practice quiz first. Let's get back to the thing here. So we're looking at solubility and Ksp. Let's look at the practice quiz here. Okay. So here's the example. A compound has the formula AOH5. Okay. If the Ksp is 8.42 times 10 to the negative 21, find the POH of a solution of this compound. All right, so let's see how we would go about this. AOH5, if I drew a picture of it, would look like this. It'd be A5 plus and then 5 OH minuses. Does anybody have any questions about this so far? Okay, so if I drew a table that related to this, it would be looking like this. AOH5 goes to A5 plus 5 OH minuses. The initial, and that's going to be solid, of course. So the initial concentration of a solid is not there because you can't find the concentration of a solid. The equilibrium concentration again is going to be just a line there because we can't find the concentration of a solid. Then it's going to be Z, and this will be 5Z. Does anybody have any questions? Okay. The Ksp is going to be based on the dissolved ions, be A5 plus, and then OH minus to the power of 5. So if I go ahead and substitute in what I have, it would be 8.42 times 10 to the negative 21. Is equal to Z times 5Z to the power of 5. Now I need to solve for Z, and Z is going, well, let's we'll run this out a little bit here. 8.42 times 10 to the negative 21 is going to be Well, let's have a look. 5 to the power of 5. Where's my calculator? Here we go. 5 to the power of 5 is 3125. And that'll be z to the 6th. So z is going to equal the 6th root. Actually, I'll do that a little bit differently. It'd be 8.42 times 10 to the negative 21 divided by 3125. And that is to the power of 1/6. Okay, I'm going to stop there for a second. Does anybody have any questions? All right, so let's see how that goes. Be 8.42 times 10 to the negative 21 divided by 3125 equals. Now that gives me the value there. Now I need to find the 6th root of that. On this calculator, I can use the y root of x, and you could probably do the same on yours. And the other one you can do is you can do to the power of and make it 1/6. So what I'll do is I will, for this one, there is no caret button on here. All I can do is this kind of thing. So let's see, we'll do x to the y. And that would be, and I'll do, so what I did was I did that number, now x to the y, and now the 1 divided by 6, close parentheses, and hit equals. And that gives me my value of z, which is 0.000117 molar. Now that's not the concentration of OH minus. If you look here, the concentration of OH minus is 5Z. So the concentration of OH minus up here, this is a step that people often forget, 5Z is 5 times 0.000117 or 118, we'll say. Which comes out to be 0.000589 or 590, we'll say. And then the POH would be the negative log of that, which I would just take the log here, and it comes out to be 3.23, and you can see that would be the answer that we would put in right there. So the POH is 3.23. Anybody got any questions? Any questions? Okay. All right, so that's the practice quiz. So nobody has any questions about that, hey? All right. Let's go back to the ungraded copy of the practice quiz. We'll take a look at the kinds of questions you're going to see. Okay, so the first few questions will be directed to breaking things up and then having the right charges on things. So for the first one here, the question is, how does SN3PO44 break up in solution? And along with this, I do give you a list of possibly relevant polyatomic ions. So these are not ones you have to memorize. You might have to know the charges on certain things on the periodic table, and I'll give you some ideas about that. Now, this is something that should be familiar to you, and that is that group 7 is going to be 1 minus, group 6 will be 2 minus, and nitrogen will be 3 minus, so you should know that. That would be the only thing I think you should know, because everything else is given to you here. So what I would do is I would draw out a picture of it. So it'd be SN3, so 3 SNs, and then we got 4 PO4s here. Any questions so far? What I would do is look at what the charge of PO4 is. You can see it's -3, so that's not something you had to memorize. And there's going to be -12, and then +12. So -12 has to match +12, which makes all of these 4 plus. So the final equation here is going to be 3 SN4 plus 4 PO4 3 minus. In the box, you would write 3 SN4 plus 4 PO4 3 negative. Does anybody have any questions? Next one, Cu3N. Now, per what I had said earlier, I'll take this back a little bit here. Looking at the periodic table, N is in group 5, so it's a -3 charge. Anybody got any questions about that? Okay. Remember, you'll have the option, you'll have the ability to do this as well, because on the test you'll have that the polyatomic ions, and you'll also have the periodic table too. But to see if we can, let me get to question here. Yeah, Cu3N. So Cu, Cu, and Cu, and N. The N is going to be a -3 charge, which means the total is -3, which means the total positive side is going to be +3. So each of those must be 1 plus. So the final equation there, 3 Cu plus N3 minus. Anybody got any questions? Okay. All right, I like this one here. This is a good one too. All right, I'm going to do a poll here. Some of you might even already know what I'm going to put down here as the poll, but we'll see. Okay. So in that, let's go back to it. It's let me write down or show you there it is, CRPO3. So I'd like you to see if you can respond to that. Can you not see the poll? Nobody's responded. Okay. Okay. There's only 14 people on the call, 13 actually, including 14, including me. Or maybe not. I don't know if that includes me. It probably doesn't. Okay. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. I'll end the poll here. Share the results. Yeah, so the answer is 1. There is one CRPO3. There's one PO3 grouping in CRPO3. So if I drew a picture of it, that's exactly what it would look like. So you'll notice that a couple of people did say 3, and that is a fairly common wrong response that I get to this. But yes, this is PO3. If there was more than one PO3, how would you know? Can anybody tell me? If there was more than one PO3 group.
Brackets.
There were brackets around what?
PO3.
PO3. So it would look something like this. CR, we'll say CR3, PO3, 2. That would indicate there were 2 PO3 groups. So this is a common thing. This 3 here is belonging to the entire polyatomic ion. So when you split it apart, then it just becomes one PO3 grouping. I kind of like that question. It's a good one that really does illustrates well what's going on here. So it would be let's see, so the picture would be CrPO3. The charge is -3, and that's from the polyatomic ion that we see here, PO3 3-. And what that means is the total charge then is -3. Total positive charge then is +3, and that would be Cr3+. So the formula here, Cr3+, and oops, I'll go ahead and just put it in the initial form here, PO3 3-. Does anybody have any questions? Okay. Well, with this one, that's a lucky break, isn't it? There's an example here for this very problem, and that would be 3 Sb5+ and 5 PO4 3-. But I'll show you how that would come about. I probably should take that question out since it's already answered in the examples. But it would be Sb, and there's 3 of those. And you can see here there's going to be 5 PO4 groups. So that's an example of what happens when you've got more than one of those polyatomic ions. I will do one more example in a second here, since it didn't kind of pop up. And that's 3 negative, 3 negative, 3 negative, 3 negative, and 3 negative. That's -15, which makes this +15, which means that the SBs are going to be 5+ each. So that would be 3 SB 5+ plus 5 PO4 3-. Anybody have any questions? All right, let's see something else here. Let's say, well, let's look at NiCl3. I have got an example here, NiCl3. So NiCl3 would break apart. We've got Ni and then 3 Cls. Now, I want you to see the difference. I want you to, this is where people get confused. See, NiCl3 would be Ni and 3 Cls, yet CrPO3 would be 1 Cr and 1 PO3. That's where people get confused. What's the difference here? Why do I handle NiCl3 differently to, or apparently differently to CrPO3? Anybody tell me?
Because PO3 is a polyatomic ion.
Right, and Cl is not. That's why we know there's 3 of them. Does anybody have any questions? Okay. So you'll do those questions. Now the next one here is a slightly soluble salt, has the formula AB1, and the Ksp is 2.0 times 10 to the negative 26. So I'm going to go ahead and do this example. So it's AB1, which is going to split into, well, if we draw a picture of it, it would be A and B. Now, as far as the charges go, you can assign whatever charges you like, but I think it would be fair enough to go A plus and B minus. Be like, NaCl, for example, be similar to that. So we do our initial molarity and equilibrium molarity. And that'll be the line here for the solid. And then 0 and 0 for the A plus and the B minus. And Z for what they break apart into. So it's going to be equal amounts of A plus and B minus. We don't know what Z is yet, but we're going to solve for it. The Ksp is going to be A plus times B minus for this one. And that's going to be Z squared. And the Ksp you're given here, 2.0 times 10 to the negative 26.
I have a question.
Yes.
Why is it Z squared and not 2Z?
Because if you look at the Ksp, it's A plus times B minus.
Oh, okay.
Right, so it's going to be Z times Z, which is Z squared. So
Okay.
Z is going to be the square root of 2.0 times 10 to the negative 26. And we'll take the square root. Now, I'd have to go ahead and count all those zeros on this calculator, but I don't know if there's a way to convert it into exponents. But anyway, let's have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it'd be 13. So I think it'd be 1.41 times 10 to the negative 13 molar. Now Z happens. Sorry, I'm sorry.
I got just a quick question.
Yes, Emmeline.
Regarding the sig figs, does it actually matter on this one? Because
Oh, not really. I should just make it 1.4. Hey. Thanks.
Oh, okay. So, okay.
Yeah, I should just make it 1.4. Sorry, I didn't. So it's Z. Now, Z is equal to, or let's put it another way, the concentration of B minus is equal to Z. So that's going to be 1.4 times 10 to the negative 13. Now, PB is going to be the negative log of that. So just take the log, and it comes out to be, well, 12.85. That is the correct number of sig figs, by the way, this time, Emmeline. That'd be 12.85 would be PB. So little p, big B is not lead. It's the negative log of the concentration of B minus. Does anybody have any questions?
So just to make sure, the only time it would be like 5Z or 2Z, like the coefficient in front of Z, is if there's an
That's right, but you would have to also include that in the penultimate step, you know, step just before the last step. You'd have to figure out that what that 5Z actually was, Jiz.
Okay.
In this case, it wasn't necessary because B minus was Z, and then there wasn't a coefficient. Sometimes there is. You do have to take that into account.
All right, thank you.
All right, no worries. Any other questions? So it's not always 1. Sometimes it's 2, 3, 4. You need to be prepared for that. Okay. Any questions? Okay. So one other question that we can ask is whether precipitation will occur if we take, for example here, a solution that contains, say, Mg2 plus, let's make it a bit bigger here, and we'll say Cl minus and Cl minus, and we'll say sodium hydroxide, Na plus and OH minus. So the Mg2 plus and the OH minus will interact, and we'll get this MgOH2 solid, which will be a precipitate. And that precipitate will be subject to this equilibrium expression. So in the end, you add them together, and maybe you'll get a precipitate, and maybe you won't. But the precipitate will be on the bottom here. We'll have Na plus and Cl minus ions in solution. Those are spectators. And down the bottom here, you've got your solid MgOH2. Does anybody have any questions so far? Okay, excuse me for a second. I need to check on something. I'll be back. All right. Sorry about that. Okay, so we've got our precipitate here, which can break apart here once it's formed. And you'll notice the Na plus and the Cl minus are still going to be in the solution. They're spectator ions. We're not interested in their concentration. Now, here's what's going to happen. We have this Ksp as being the Mg2 plus times the OH minus squared, which hasn't changed. And then that's what happens at equilibrium. But if you remember, our friend Q is the reaction quotient, which allows us to determine what the situation is at any time, not just equilibrium. And this is only at equilibrium. That's because that's an equilibrium constant. So the situation is, if we're looking at this as being the reaction here, and that's the Q expression, it's kind of like, you can look upon it this way, but you don't have to. I'm just giving you an example here of a way you can look at it. OH minus squared over MgOH2 solid. And you can ask the question in relation to Ksp, what's going to happen to Q? So if Q is less than Ksp, precipitation won't occur. Now the reason for that is because if Q is less than Ksp, the top portion is going to get bigger. That's the Mg2 plus and the OH minus. That happens to be the ionic side of the equation here. So the ions, there's going to be more ions there, so precipitation won't occur. Now, if Q is greater than Ksp, what that means is this bottom one, MgOH2 solid, is going to have to get bigger so that Q gets closer to K. So what that means is that the precipitation will occur because we're going to be more on the solid side. So this is precipitation with the solid, and this is no precipitation on this side. Because what we're talking about there are dissolved ions. Does anybody have any questions about what I'm telling you here with the Q being less than or greater than the Ksp? Okay. So we did do problems like that way back in test 1. So let's look at the kind of problem that you'll face on the test, and it's going to be a combination problem, and it's going to be something like this. It's determined if precipitation will occur of in this case, the Ca3PO42 solid when 10.0 mils of 6.00 times 10 to the negative 5 molar CaCl2 is added to 100.0 mils of 5.00 times 10 to the negative 7 molar Be3PO42. So the situation is this. We've got a solution here of CaCl2, aqueous, and we have a solution here of Be3PO42, and that's aqueous as well. And by aqueous, there's not going to be any solid present. These things get added together, and you know that's going to be a certain volume. This volume here, well, let's make it real. We'll say 10.0 mils. This is 100.0 mils, I think, yes. And the solution here is 110.0 mils. So you can see that the volume is changing. It's going to be the sum of those two volumes that we're getting here. And then we're going to get possibly a precipitate, and that precipitate, according to the problem, may be Ca3PO42. So we're trying to determine whether this precipitate will actually form or not. So what that means is we're going to have to calculate Q, which is going to be the concentration of Ca2 plus cubed PO43 minus squared. Does anybody have any questions? Okay, so we have to determine this concentration of Ca2 plus and this concentration of PO43 minus. Is everybody okay with where I'm getting the cubed and the squared from? Everybody okay with that? Anybody have any questions?
So where exactly are you getting those from?
Do you see the equation you're given with the calcium phosphate?
Right.
Yeah, so this is the Ksp that you're given here, 1.00 times 10 to the negative 25. And then this is going to be Ca2 plus to the power of 3 and PO43 minus to the power of 2. So it's all based on the equation that you're given here.
Oh, okay.
All right, but you still have to find these two values here, the Ca2 plus and the PO43 minus. So I'm going to open up a new window here. So what we have to do is we have to, first of all, look at the initial solution, which just contains CaCl2, so that we can determine the concentration of Ca2 plus in that. Now, if you look at the CaCl2, it breaks apart into Ca2 plus and 2Cl minus. So if you drew a picture of it, it would be Ca and 2Cls. Each of those has a -1 charge and Ca has a 2+ charge. We're only interested though in the Ca2 plus. And the reason for that is because the precipitate is calcium phosphate, which doesn't contain any chloride. So the Cl is going to be a spectator ion. We're only interested in the calcium 2 plus. In order to calculate the Ca2 plus in solution here, we're going to have to look at the molarity and then multiply it by how many calciums we get when that CaCl2 breaks apart. Now, it won't always be a one-to-one situation, but it's going to be molar CaCl2 plus, no, sorry, times 1 mole of Ca2 plus over 1 mole of CaCl2. So we're just doing a little bit of stoichiometry here. And that comes out to be 6.00 times 10 to the -5 molar. So it hasn't changed at all, but that would be because when it breaks apart, it just breaks apart into 1. That's not always the case. The other thing we have to do is then account for the dilution factor. Because if you remember, let's go back to the initial problem here. We take the initial solution, which I've already found the concentration of calcium 2 plus in there, and now because it gets diluted down to 110.0 mils from 10.0 mils because we're adding two solutions together. In order to take account of this, we use the dilution equation, which is C1V1 equals C2V2. The C1 is going to be the 6.00 times 10 to the -5 molar multiplied by the initial volume of that. Now it's going to equal C2 times the total volume, which is 110.0 mils.
I have a question.
Yes. Yes.
Where did you get this 6 times 10 to the -5?
Okay, look at do you see the initial problem here? It tells us
okay.
right, the concentration. And then
Okay.
1 to 1, so it turns out to be the same concentration of calcium 2 plus as it was CaCl2.
Okay.
All right, so that goes in here as C1, all right? Now C2, when we solve for it, is going to be 5.45 times 10 to the -6 molar. Okay, is there any questions so far? So that happens to equal the concentration of Ca2 plus in the final solution.
So how did you get the 5.45 times 10 to the -6?
Okay, so 6.00 times 10 to the -5 times 10 divided by 110.
Divided by 110. Okay.
You see it's on the other side. We're just isolating C2.
Okay.
Is that all right?
That's good.
Okay, any other questions?
I was wondering how, going back a few steps for the 6.00 times 10 to the -5 for molarity of CaCl2, how does that cancel out with the moles? Because isn't it moles?
Well, Oh, how does the mole, well, okay, think of what M is. M is moles per liter, right? So it's moles CaCl2 per liter, right? That's what big M is.
Mhm.
So the moles of CaCl2 cancel, and you'll end up with moles of Ca2 plus per liter, which is still here.
Okay.
And that's why we get big M down here.
Okay.
Is that
you.
okay?
Yes. Thank you.
All right. Any other questions? Yes.
Yeah. Is it always a 1-to-1 ratio, or
no,
is
it
that going to
isn't.
be given?
No, you'd have to determine that, Alexandra, and you do that by looking at the initial equation. I'll show you in the next one that isn't 1-to-1, okay?
Okay.
Okay, so in this next part that's coming up, that's what we're going to look at. So let's look at it in another page here. And what we're looking at here is, and I'll bring this onto the next page here, is we're now going to focus on the Be3PO42. So remember, we've got 100 mils of this, and it's Be3PO42 in solution. And when I draw a picture of that, it would be 3 BEs and then 2 PO4s. Each of those is -3, and the BEs will be 2 plus. Now you might be wondering, well, how would you know what the PO4 3 minus was? Well, look at the initial equation. I tell you what phosphate is. So PO4 is 3 negative. That's how you get the 2 plus on the BE. Now the BE is going to be a spectator ion. So the equation is going to look like this. So that's the breaking up equation. We're only interested in the phosphate. We're not interested in the beryllium. Now you might be wondering, how do I know we're not interested in the beryllium? We'll take a look at the, let's go back to the first thing here. What I had said was that because of this, we're only interested in the calcium and the phosphate. Let's go back to Untitled 3 here. Okay. Does anybody have any questions? Now, in this case, Alexandra, I'm going to answer your question now. You can see that the mole ratio is 2-to-1. So it's not always 1-to-1. So it'll be 5.00 times 10 to the -7. That was given in the problem. And that's the Be3PO42.
Thank you.
And that's times 2 moles of phosphate, you're welcome, per 1 mole of the Be3PO42. And that would be 1.00 times 10 to the -6. And that's PO4 3 minus. And then we need to, again, concentrate on what happens to the dilution. And that's going to be 1.00. Remember, we're using this particular concentration for PO4 3 minus, not the initial one. Then to -6 molar times 100.0 mils equals C2, again, times 110.0 mils. All right, so let me show you where those numbers come from. The 1.00 times 10 to the -6 comes from here, the concentration calculation we just did. The 100.0 mils comes from the initial question, which stated 100.0 mils of the Be3PO42 was added. And what that means is that C2, which is the concentration of phosphate, is going to be 9.09 times 10 to the negative 7 molar. Does anybody have any questions?
I'm a little confused on why in this one, or like the other one, we had to add 100 plus 10 milliliters, but for this one, we just left it. Oh, wait, now I see it. Never mind. I was
And if
reading.
there's your 110 over here, Jiz,
I see.
right? That's always going to be a V2, the total volume, because we're trying to determine, it starts at out 100.0 and then it goes to 110. So
Okay.
we're dividing by 110. That gives us this final volume here, which actually isn't too far different from the initial one, really, but it is a little different because it's now 100 going to 110. Does that make sense?
Yeah, thank you.
Okay. Now going back to the original thing here, the Q expression we're looking for is going to be Ca2 plus cubed PO43 minus squared, based on the equation that we're given, because you are given this equation here in this problem. So the Q is going to be we're going to substitute those values in. So that would be 5.45 times 10 to the negative 6. And that's cubed times the 9.09 times 10 to the negative 7. And that's squared. And this comes out to be 1.33 times 10 to the negative 28. And that's how you calculate the Q. And then to figure out if precipitation occurs or not, look at the Q value compared to the Ksp value that's been given here. And it comes out to be less than 1.00 times 10 to the negative 25, which means that precipitation won't occur. Does anybody have any questions?
So I get all the steps. Where'd you get the 5.45 from?
That's the calcium concentration that we got. Let's see, I think it's Untitled 2 here. There we go, down here.
Oh, from the previous problem that we just did.
That's right. So we have to figure out each one of those separately, okay?
Okay, that makes sense.
Okay. The question you'll see, I'm actually going to leave number 25 to you to figure out which answer is going to be the right one here. Let's look at this. I really like this example here. This is a good one. We've got the solution of AB5 and a solution of CD2, and we're looking for the PQSP of AD5. So this is just looking for the Q value and it's stopping there. It's not asking if precipitation is going to occur or not. So what we need to do is come up with these equations here for how they break apart. So we're going to have AB5, and we're going to have, what is it, CD2. And we're looking for the precipitation, possibly, of AD5. So that's the precipitate there. And that's what we're told. We're told this in the problem. Okay, any questions so far? So AB5 is going to split into A 5 plus and 5 B minuses. Now the charges really don't matter, but the coefficients certainly do. Now what are we interested in here? We're interested in the concentration of A from that one, and from the other one, which is CD2, we know that's going to be C2 plus 2D minus, and we're only interested in the D out of that. Does anybody have any questions? Okay, so let's look at the AB5 first. Let's see, I think I might have a, yes, no. So we're looking at AB5. Which I said is splitting into A5 plus. And remember, the charges don't matter. It's really just A and 5Bs. If you want to be really simple about it, that's okay. So what we're doing here is we see that it's going to be 0.00350 molar, and that's going to be AB5. And according to the equation, we're going to get 1 mole of A5 plus, which is what we're interested in here, remember, over 1 mole of AB5. So it is just going to be 1 to 1, which is 0.00350 molar. And that's going to be A5 plus. Now we're interested also in the concentration after it's been diluted, and we're going to have 0.00350 times 120.0 mils, 00 mils, is equal to C2 times the total, which is going to be 510.00 mils. So the new concentration of A5 plus after dilution is going to be, let's have a look, uh, 0.00824. 0.000824 molar. Does anybody have any questions? Okay. Now the next one is the CD2. Because that's the initial thing that we're talking about. And it's 0.00150 molar CD2. And we're interested in, well, we see it's going to be 2 moles of D for every 1 mole of CD2, which is going to be 0.00300 molar. And that is D, which is going to, we'll make a D minus here. So that's initially the concentration. Then we need to look at the dilution. So going back to where the 2 moles comes into play. All right, I didn't draw a picture of it. I'll draw a picture of it here. So CD2, I might have drawn a picture somewhere else, is going to be C2 plus 2D minus. That's the reaction. We're only interested in the D's though. So that's going to be 0.00300 molar times the volume, which is 390.00 mils. So that's what we're given in the problem. Equals C2 times the total volume, which again is 510.00 mils. So that would be 3 times 390 divided by 510. Okay, that's 0.00229. And that's going to be our final concentration of D minus. Whoops, D minus. Okay, does anybody have any questions so far? Now we're looking for AD5, and that's according to the problem there. And AD5 is going to be A5 plus 5D minus. Notice that's different to CD2 that broke apart. The Q value is going to be A5 plus times D minus to the 5th. The A5 plus is what we got, let's see, it would have been, I think, an Untitled 2, Untitled 3, there we go. 0.00824 molar. Let me see, look again, is it 0.000? Yeah, 0.000. I think it was 842 molar. Times D minus, make sure it's 842, it's 824, sorry about that. Times the D minus, which we get back from here, which was 0.00229, but that's all to the 5th. Which comes up with our Q value. And that's to the 5th. And we get 5.18 times 10 to the negative 17. And the PQ, or 5.19 we'll say. And the PQ then would be, take the log of that, and we get 16.285. Which would be the answer you'd put in the box. Okay, any questions? Okay, well, we're going to do a review on Tuesday, so we'll be going through this test. And it's a pretty, well, there's a lot to do. So make sure that you do get a start on it. Don't leave it all to the last day. You'll be sorry if you do. You will fail. I mean, it's a predetermined fact. You will fail if you leave this until the last day. So it's time to get down and do some work, do some extra credit quizzes as well, and make sure that you have knowledge of what you're doing. If you need any help, send me an email, give me a call, whatever you need to do. Or you can also talk to the folks on tutor.com as well. All right, does anybody have any other questions? Okay, we'll leave it there. Thank you, and I will see you on Tuesday. Have a nice weekend.